All right, we're going to kick this week off with a discussion on finding the determinant of a matrix. So the determinant of a square matrix is going to measure the n-dimensional volume of the parallelepiped that is generated by the column vectors of A. If none of that sounds familiar, it's because we're not going to spend a whole lot of time talking about the geometric interpretations of what a determinant is. So not only can we find a determinant to kind of talk about some interesting geometric things that are beyond the scope of this class, we also can use them for computational purposes, and they're going to be kind of a main thing we need for some of the stuff later in this week. So let's talk a little bit about some of the properties of determinants that we can have, and then after seeing some examples of how to find determinants kind of the long way, we'll do it a little bit faster. So let's talk about these properties. So the determinant is a number where if alpha is a scalar, the determinant of a matrix is going to satisfy all of these properties. The determinant of some matrix A times this alpha that we're trying to find the determinant of is going to be equal to alpha to the n power times the determinant of that matrix. If we take the determinant of A transpose, it should be the same as the determinant of the matrix. If B is obtained by obtaining or performing a row operation on matrix A that involves adding a multiple of one row to another row, then the determinant of B and the determinant of A are going to be the same. If we obtain B instead by performing a row operation where we multiply a row by some scalar, not add a multiple, but just multiply a row by a scalar, then the determinant of B is going to be equal to the determinant of A, but times whatever scalar it is we got to obtain the matrix B. And then last but not least, if we perform a row swap, so we switch two rows in order to get matrix B from matrix A, then B is going to be equal to -1 times, or the determinant of B will be equal to -1 times the determinant of A. And if a matrix is in echelon form, then the determinant of the matrix is just the product of the diagonal elements. So we can use these to find the determinant of a matrix by just kind of keeping track of what row operations we do. So let's kind of see a couple of examples of this. So if we wanted to find the determinant of this matrix, what we'd want to do is we'd want to reduce A into at least echelon form. And from there we can go ahead and also keep track of what our row operations are and see how our determinant should change. So if we start off with this matrix, A, and we're trying to find its determinant, right now the determinant should not be impacted in any way, shape, or form. Now if we go ahead and we perform row operations in order to get, since we have a 1 up here, we want zeros below it, so here we're just adding multiples of rows. Now adding multiples of rows to other rows does not change the determinant, so this is fine. We also will then go ahead, and since we'd like to have a 1 here, we'll go ahead and we'll do kind of a little bit of a strange operation for us. We will add a row to the third row to the second row to get this row, and once again, adding multiple of row does not change the determinant. We then can go ahead and multiply this, since it's a +1, by -1, and that'll give us a +1 there, and then we can also go ahead and perform a row operation to zero out the term below it in the column. But since we've multiplied by a -1, we have to multiply by the determinant by -1. And then last but not least, we have this -1 down here, and we'd like to be able to make our multiplication a little bit easier, so we can multiply by -1 again, and that'll give us a +1, and it also changes the determinant back to what it was. So that means that the determinant of A, because it's now in echelon form, is just the product of the diagonal elements. So it'll be 1 times 1 times 1, which is just 1. All right, so that's one example. Let's see another example. So let's go ahead and take a look at this matrix and try to find its determinant. So we're going to start with this matrix. Again, we keep track of our changes to our matrix through the row operations. So here we start off with just its normal determinant. If we multiply a row by a half, we have to go ahead and multiply the determinant by a half. row combinations don't change anything. Multiplying by a -1 gives us -1/2 determinant of A, and then if we multiply a row by -1/2 again, -1/2 times -1/2 will be positive 1/4. So now the determinant of A will come times 1/4 will equal this product. So 1/4 determinant of A should equal 1 times 1 times 1, which is 1, which tells us then that the determinant of this matrix equals 4. All right, well, that all seems tedious. So fortunately, that's not the only method for finding a determinant. There's another method called cofactor expansion. And before we talk about cofactor expansion, we're going to show just the formula for finding the determinant of a 2 by 2 matrix. And if you remember trying to find the inverse for a 2 by 2 matrix, this formula might look a little bit familiar to you. So let's say we've got a 2 by 2 matrix, A, B, C, D. The determinant of the matrix will be found by taking A times D minus B times C. So we take the main diagonal entries, multiply them, and subtract the off-diagonal entries. Note that the determinant of a matrix will sometimes be denoted as what looks like the absolute value sign around the matrix. This is just a notation you might see out in the wild, so be wary of this existing. All right, so let's then try to find the determinant of this matrix. It's 2 by 2. Following along with that formula, we'll take 5 times 3 minus 4 times 1. So that'll be 15 minus 4, which will give us 11. So our answer should be B. Now, if we have a matrix that's bigger than a 2 by 2, we have to do something a little more involved. And this is going to be something called cofactor expansion. So we're going to let A be an n by n matrix, and we're going to choose any j such that j is between 1 and n. It can include those. What we're going to do is we're going to find the determinant by taking the summation of -1 to the I plus j times aij times the determinant of mij, where mij is the submatrix of A, where the ith row and jth column has been removed. Formulaically, that seems like a mouthful, but what we're really doing is something kind of a little more easy. So let's see a couple of examples of trying to find the 3 by 3 matrix using cofactor expansion. So there's no numbers here, but there's multiple ways to do this cofactor expansion. So what we can do is for the cofactor expansion along row 1, what this formula says is we need to take whichever row and column we are in, add those up, and raise that to -1 to that power, multiply by whatever entry is in that position, and then find the determinant of the matrix that is found by removing that row and column. So if we want to go along row 1, we will take -1 to the, if we're taking A as our first entry, A is in the first row and first column, so -1 to the 1 plus 1 power times A times the determinant of the matrix we get by removing the row and column A is in, so E, F, H, I. And then we need to add -1, and if we're going along the first row, what we'll do is we'll take this B, and since it is in the first row and second column, we will raise -1 to the 1 plus 2 power, multiply by B, and then multiply that by the determinant of the matrix we get by removing the first row and the second column, so D, F, G, I. And then we will add -1 times, since we're going to use C next, it's in the first row and third column, so 1 plus 3 times C times the determinant of the matrix we get by removing the first row and the third column, so D, E, G, H. And then these individual determinants here, these 2 by 2 determinants, are things that we should know how to find on our own, because we have a formula for the 2 by 2 determinant, which is going to help us quite a bit. All right, so let's talk about what's going on here. When we're looking at these negative ones to the whatever power, what you should notice is that since they're going and changing by 1 each time for their exponents, we're really having alternating signs here. So if we're using this first entry, because it's in the first row and first column, this is going to be a kind of positive sign. I'm going to draw a little table for us here. So this will always be a positive sign if we're using it for the cofactor expansion. If we're using the first row second entry, negative 1 to the third power, or to an odd power, will be negative. And then since this power will be even, it will be positive. And then if we kind of continue down the column, so here, first row, first column, second row, first column will be odd, so it'll be negative. Third row, first column will be even, so it'll be positive. And this pattern of negative positives will continue throughout the entire matrix. So if we wanted to go ahead and do a cofactor expansion along a different row, so this will be example 1. Example 2. Now let's go along row, 2. What we'll get is we will have the first entry, which is D. Because we're going to have an odd exponent for the negative 1, it'll be negative D, and then times the determinant of the matrix we get by taking out the first column, because that's where D is, and the second row, because that's where D is. So we have B, C, H, I. And then it'll be plus E times the determinant that we get by taking out the second row and second column. So having a little trouble getting both crossed out, covered over here. Let me see if I can grab another pen. Will this help? And not as much as I want it to. So ACGH will be our next little determinant. Or sorry, ACGI. I misspoke. And then since we're going to minus now with the F, so minus F times the determinant that we get by taking out the second row and third column, so ABGH. Okay, now we don't just have to do this along the row, we also can do it along a column, and each of these is going to be equal to the same thing. The way we derived our formula or ordered things is a little different, but we should still get the exact same output regardless of which method we use to find the determinant. So let's go ahead, and for one more example, I'm going to go ahead and go along column 2. So if we go along column 2, we want to go B, E, and H as our coefficients. And for these, the signs, because we're going down that second column, will be negative, positive, negative. And then all that's left to do is to go ahead and determine what determinants we're multiplying each of these by. So for B, we take out the second column and second row. So this will be, the first row and the second column. So it'll be DFGI plus E times, since it's in the second row, second column, it would be ACGI that is left. And then for H, because it is in the third row and second column, we'll be using ACDF. All right, so this is just kind of how we would look at it and justify it from a standpoint of here's how we go ahead and use this formula with some examples. Let's go ahead and actually put in some numbers though. So when we're trying to calculate the determinant of A when we have some actual numbers, one of the first things I like to do when I'm calculating these determinants is kind of refresh myself, depending on which row or column I want to use, what the cofactor expansion is going to cause the sign to be. Because this is usually the hardest part, right? Remembering the -1 in the formula is a little tricky, and so what we want to do is we want to just kind of write this kind of quickly to ourselves so we kind of remember what we need. Now we can pick any row and column we'd like. I'm going to go ahead and use the first row first, and then I'm going to also show you what happens if we use, say, the second column. Because there's a little bit of a trick, or you know what? Yeah, I'm going to use the first column first, and then I'll use the second row. Because there's a little trick to kind of picking which row or column you want to use. So if we used column 1, making decisions on the fly, that is a poor choice. So if we're using this column, our coefficients are going to be 2, 1, and -2. And our signs should be positive, negative, positive. So positive, negative, and then this was already a -2, so -2 and then plus will still be negative. And then we need to multiply by whatever our proper determinants are. So if we take out the first row, first column, where that 2 is, we should get 0, 1, 2, -4. If we take out where this 1 is, we should get 2, 2, 2, -4. And if we take out where this -2 is, we should get 2, 2, 0, 1. Now our next step is to go ahead and calculate these little subdeterminants. So we've got 2 times 0 times -4 minus 2 times 1 minus 2 times -4 minus 2 times 2. It'll be very tricky to keep track of all of your signs as you do all of this. Please be careful. Times -2 times 2 times 1 minus 2 times 0. Okay, so go ahead and simplifying all of that, we get 0 minus 2, so we have 2 times -2 minus 1 times, this will be -8 minus 4 minus 2 times 2 minus 0, so just 2. So this will give us -4. -1 times -12 will be plus 12, and then minus 4, so we should get a determinant in the end of 4. So that was one way of finding this determinant. We also could go ahead and try to pick something where our coefficients are going to be helpful to us. So if we don't want to have to remember to multiply by these 2's, or we want something with easy signs, or we'd like to be able to multiply by 0, because that'll get something to disappear, then we can kind of make intelligent choices about where we're doing our cofactor expansion. So let's use the second row, because I like these 1's a little better than I like the 2's, and this 0 is something that's very helpful to us. So if we're going along row 2, then we want to go ahead and start off with 1, 0, and 1, which are going to be our coefficients along that row. Because we are using the negative, positive, negative from the second row, we should have minus, plus, and minus. And then we need to figure out what our determinants are when we take away that row and column. So if we take away the first row and the second row and the first column, we get 2, 2, 2, negative 4. If we take away the 0 row and column, we should get 2, 2, negative 4. And if we take away the second row and the third column, we should get 2, 2, negative 2, 2. All right, so let's go ahead and calculate these little determinants. So we get negative 1 times negative 8 minus 4. So it'll be 2 times negative 4 is negative 8, minus 2 times 2, which is 4, plus 0 times, honestly, who cares? Because it doesn't matter what this determinant is. If we multiply it by 0, it's going to become 0. Minus 1. 2 times 2 is 4, minus 2 times negative 2 is negative 4, so we're subtracting a negative 4, so it'll become positive. All right, so we get negative 1 times negative 12 plus 0 minus 8. So we get 12 minus 8. So again, we get 4. So both of these, same answer, same determinant. It doesn't matter which cofactor expansion you use, you should get the same thing. But we can make some choices that make our lives a little bit easier to work with if we think about it for a little bit. So that's something that we can take advantage of. All right, now what would happen if we wanted to do a 4x4 matrix? So let's say we had something like this, where we had they're subscripted by which row they're in and which column they're in. So again, if we wanted to do kind of our cofactor expansion, we're going to have these alternating signs to worry about. And so if we went ahead and we did a cofactor expansion along the first row for simplicity, then we would take A11 times the matrix we got by removing that, which would be this matrix right here, minus A12 times the matrix we get by removing that row and column, which would be this one, plus A13 times the matrix we get by removing that row and column, plus or minus A14 times the matrix we get by removing that row and column. But then we'd have to calculate each of these 3x3 determinants. So for this one, we could do another cofactor expansion, where we had really A11 times A22 times the determinant of A33. I'm going to stop putting, well, I won't stop putting commas. A34, A43, A44, minus A23 times the determinant of A32, A34, A42, A44, plus A24, are we having fun yet? Times A32, A33, A42, or rather the determinant times the determinant of this matrix, A43 minus A12 times, and there's a lot more to go on. But you see how it would be kind of a very tedious process to keep going kind of beyond a 3x3. All right, so what I'd like you to do is, having seen all of this, I would like for you guys to look at the next 3 examples. Maybe take a moment to pause and see if you can come up with these 3 determinants on your own. All right, cool. You picked your favorite cofactor expansion? Excellent. I'm going to go ahead and pick my own favorite row or my own favorite column to do these, but it doesn't matter which one you pick. you'll get the same final answer in the end. So if we want to go ahead and do the determinant of this matrix, we should pick a row or column. So again, remind ourselves that we have all these pluses and minuses to worry about. I want to use column 3. So if I used column 3, I should get, using this column, 0 times the determinant of something when I take these rows out. So 1, 3, 0, negative 1, minus 2 times the determinant of 5, 1, 0, negative 1, plus 1 times the determinant of 5, 1, 1, 3. All right, so when we do all that, we should get 0 minus 2 times negative 5 minus 0 plus 1 times 15 minus 1. So we should get 10 plus 14, which is 24. So our answer for the first one should be C. All right, so we can pick whichever row or column we'd like for our determinant. I'm going to go ahead and pick the first column for this second one. So using column 1, again keeping in mind the pluses and the minuses, we should have 5 times the determinant of 3, 4, 0, 1 minus 0 times the determinant of, it doesn't really matter, who cares, but just for practice, 2, negative 1, 0, 1 plus 0 times the determinant of 2, negative 1, 3, 4. So that'll give us 5 times the determinant of 3, 4, 0, 1, which will be 5 times 3 times 1 minus 4 times 0, or just 5 times 3 times 1, which will be 15. C. But notice that because of all these zeros, it didn't really matter what we chose for these. And because we had another 0 below the diagonal, when we got to this determinant, the thing that wasn't along this diagonal zeroed out and got canceled out. So something we could notice here is that the determinant of a triangular matrix is the product of the diagonal entries. So that can be a nice, easy shortcut for us then if we have something that is triangular. So either lower triangular, we can do this, or upper triangular where we could, or sorry, upper triangular where we have this, or lower triangular like this one where we can get the zeros to work out. All right, so let's try to find the determinant of this matrix. So again, if we go through the first column, we'll have 5 times the determinant of 3, 0, 0, 1 minus 0 times the determinant of, in this case, 0, 0, 0, 1 plus 0 times the determinant of 0, 0, 3, 0. So this will just be 5 times the determinant of 5, 0, 0, or sorry, 3, 0, 0, 1, which will just again be 5 times 3 times 1, which is 15. So if we have a diagonal matrix, notice that a diagonal matrix is just a triangular matrix. It's both upper triangular and lower triangular. So the determinant of a diagonal matrix is again the product of the diagonal entries. So these determinants are something that are going to be very useful for us to be able to use from a computational standpoint, but they also relate a little bit to our invertible matrix theorem. So at the end of last week, we talked about the invertible matrix theorem, about how we had all of these nice properties that either were all true or all false at the same time for a square matrix. So if we wanted to find that a matrix was invertible, the thing that we're going to discover is that the determinant of the matrix then cannot be equal to 0. So this is something that there's a kind of a more drawn out proof for that we're not going to worry too much about right now. So that's the idea behind determinants.